Hello, Math 200 students. We're going to be talking about things in Chapter 4 today, beginning with sections 4.1 and 4.2. Kind of the big topic here is going to be curve sketching. How can we take all the information about a function and graph it in a very precise kind of way, and how can calculus help us to do that? That's going to take us a couple of different videos to get the full picture of that, but this will be part one, I suppose. So, absolute and relative extreme values. How can derivatives help us determine a function's extrema? All right, here is a strategy. Guidelines for finding intervals of increase or decrease. That's how we're going to first find intervals of increase and decrease. How do we find those? A lot of times what things you've learned in previous algebra classes are basically just looking at a graph. How do I look at a graph and determine the interval of increase or decrease? But now we're just going to be able to do it purely algebraically, with purely algebraic methods without having to look at graphical methods. So the algebra is going to lead to the graph rather than the opposite. So step one, locate the critical values or numbers of f. Use these numbers, these critical values, to determine test intervals. Also include points of discontinuity. So the critical points, what are critical points? Critical points are where the derivative of a function is either equal to 0 or undefined. Let me say that again. Critical points, or critical values, whatever you want to call them, are where the derivative of a function is either equal to 0 or undefined. I want to write that down. Step 2. Determine the sign of f prime of x in each interval. So you find your critical points, and that will set up intervals for you. The function is going to be either increasing or decreasing or constant over those intervals. Then you're going to determine the sign of the derivative in each of those intervals. If the sign of f prime is positive or greater than 0, then f of x is increasing over the interval, because it means the slope of that function is positive, which means the function is increasing if the slope is positive. All right, if f prime is decreasing, if f prime is negative, or in other words less than 0, then the function f of x is decreasing over the interval. And if the derivative is equal to 0, obviously the function is constant over that interval. All right, another strategy, not only finding intervals of increase and decrease algebraically using derivatives, but also finding absolute extrema using derivatives. So number one, find all critical points, as we've already said. Evaluate f at all of those critical points and at the endpoints. So we're finding the extrema within a given interval. The interval might be negative infinity to infinity, or it might be two finite limits for the endpoints. It might be from -3 to 2. So we're going to evaluate the function at all of the critical points within that interval, as well as at the endpoints of that interval itself. Let me show you why. So let's see here. So what may happen is you may have this interval, right? So maybe we have this function, but we are only interested in looking at the function within this interval. So we don't care about anything outside of that interval. We're only looking at the function within that interval. So we're just looking at this part of the function. It's the only part of the function that we're concerned with in my little hypothetical example. So we're going to find the critical points. The critical points are going to be all those points where the derivative equals 0. A derivative equals 0 where the slope of the tangent line is 0, and that's going to happen at a local minimum or a local maximum. But also we're going to look at the endpoints, because the endpoints themselves could be the absolute min or max within that interval, because they could be higher than the local minima or maxima for that. And then the other instruction says take the largest or smallest of these values. So whichever one of these is the biggest, that's the absolute minimum. Whichever one of these is the smallest, that's the absolute. I don't know if I said it right before. That's the absolute. The largest of these is the absolute maximum. The smallest of these is the absolute minimum. All right, keeping on going. Getting to an example. Number 1, find the absolute maximum and minimum values of this function, f of t equals 8t minus t to the fourth on the interval -2 to 1. So what is the first step? Identify all critical points. What are the critical points? Finding the zeros of the derivative, finding the zeros of f prime of t and or where the derivative is undefined. So we will find the derivative of this function. Let me do this by hand for you. All right, so the derivative of this function, f prime of t, is going to be, the derivative of this is going to be 8 minus 4t cubed. And we're going to, first of all, is there anywhere that this is undefined? No, there's no place where this is just a polynomial. A polynomial would not be undefined anywhere. So we just need to find where this equals 0. So move the 8 over, divide by -4, we get t cubed would equal +2. Right, move over the 8, you get -8, divide by -4, you get 2, t cubed equals +2. Take the cube root of both sides, and t will equal, we could just say the cube root of 2, or we could estimate that to be, I think I've already got it down here, so I don't have to go to my calculator, 1.26. All right, what is the next step? We've done step 1, steps 2 and 3. Evaluate f at all critical points and end points. So the critical points, we only have one critical point, the cube root of 2, and we have 2 end points, -2 and 1. Now notice, our interval, find the absolute and maximum minimum values of that function on the interval -2 to 1. So we're only concerned with the values from -2 to 1. Well, the critical value we found earlier was 1.26, which is outside of that interval. Like we're only doing the interval of this function from -2 to 1. We're only looking at the function within this part of the graph. So that critical point 1.26 actually happens somewhere out here. So we can't even look at that because that's not part of the interval that we're evaluating. So then we just throw it out. We discount it. We're not worried about that one. So then the only thing we have to do, since we don't have any other critical points, is evaluate it at the endpoints themselves. So I'm going to evaluate f at the endpoints at -2 and at 1. So at -2, we have -16 minus 16, which is 0. So we have the point -2, 0. And we have the point 8 times 1 minus 1 to the fourth. 8 minus 1 is 7. So we also have the point 1, 7. So that means which is the highest point? The highest point would be 1, 7. So that means that is a what? That is an absolute maximum on that interval. And what about this one? Well, that's the lowest point. So that is the absolute minimum on that interval. right, which is what this presentation is saying. F of negative 2 is negative 32. That's an absolute minimum. F of 1 is 7. So that's an absolute maximum. Let me see if I evaluated that thing correctly. F of negative 2. Let me try that again. F of negative 2. I might have plugged that in wrong. Is equal to 8 times negative 2 minus negative 2 to the 4th. So that's negative 16 minus 16. Yeah, that's negative 32. I said 0 earlier. I was totally wrong about that. So that's the point. Negative 2, negative 32. But regardless, that is an absolute minimum. And then when we plug in 1, we get 8 times 1 minus 1 to the 4th, which is 8 minus 1, which is 7. So we have the point 17, and that is the highest point, so that's the absolute maximum on that interval. Next example, find the absolute maximum and minimum values on this new function f of x equals x to the 2/3 on the interval negative 2 to 3. Identify all the critical points to step 1, again finding the zeros or where it is undefined. So we do the derivative, and we find the critical points by finding the zeros or the undefined points of that derivative. So f prime of x here, do the power rule. It's going to be 2/3 x to the, you got to subtract it by 1, so it's to the negative 1/3, because 2/3 minus 1 is negative 1/3. We could rewrite that as 2/3 with a cube root of x underneath there, because the 1/3 power is the same thing as a cube root, and the negative exponent moves it to the denominator. Now, we might set that equal to 0 and multiply by the cube root of x on both sides to get the cube root of x off the bottom. That gives us 2/3 equals, well, 0 times the cube root of x is still 0. And 2/3 does not equal 0. And there's nothing about x that could ever make that happen. So there's no solution to that, which means there are no zeros. That derivative function never crosses the x-axis. It never has a 0. It never equals 0. But it does, if we look back at it again, 2/3 cube root of x. It does have a place where it is undefined. In other words, where is this ever undefined? It's undefined when the denominator equals 0. And what value of x could make this denominator equal 0? Well, if I plug in 0 in there, then that is going to be the cube root of 0, which is 0. 3 times 0 is 0. So the whole denominator is 0, which means that thing is undefined at x equals 0. So I have a critical value. Okay, a critical point or a critical value would be x equals 0. So I evaluate the function. In other words, I plug something into the function. I plug 0 into the function. That critical value, that's what I plug into f. And so f of 0 would be 0 to the 2/3 power, or we could say the cube root of 0 squared, which is the cube root of 0, which is 0. So I have the point 0, 0. That's one of my candidates for the absolute maximum or absolute minimum. Candidates. In other words, possibilities. Now my other candidates would be the endpoints. I'm also going to evaluate the function at its endpoints. So I need some room to do that. Let me erase some of this to get some room. Okay, probably be enough room. So I'm going to do f of negative 2, and I'm going to do f of 3. Let's see what we get. So I've got negative 2 to the 2/3, which is the cube root of negative 2 squared, which is the cube root of, what is that, the cube root of positive 4. Which is I'm just looking back at my presentation here to not have to use my calculator, which is about 1.59. 1.59. So another candidate would be -2, 1.59. And then f of 3, that would be 3 to the 2/3, which would be the cube root of 3 squared, which is the cube root of 9, which is around about, again, I'm going back to my presentation, which is about 2.08. So my last candidate is 3, 2.08. So of these candidates, which one has the lowest value, the lowest y coordinate? That would be 0, 0. So that is the absolute minimum then. And which one of these has the highest y value? 3, 2.08. So that is the absolute maximum. So that's our absolute min, that's our absolute max. So 0, 0 was the absolute min. That was where we had a critical point. -2, 1.59 was where we had an end point, but it's not the lowest. 0, 0 is actually the lowest. So we can imagine this thing kind of going like this on that interval, where here's one of the endpoints, and here's that critical value 0, 0, and here's the other endpoint. So that endpoint was not an absolute max or min. It was that one of these interior points was lower than that, and then the other endpoint was the highest point. So that was the absolute max on that interval. All right, let's go to example 3. The function f of x equals x to the 1/3 x minus 4. Identify the intervals of increase and decrease and the absolute extrema. Okay, so again, finding the critical points. To find the critical points here, notice I don't have endpoints. So this is just I'm identifying the intervals of increase or decrease over the entire domain of the function. I think what I want to do, I could do the product rule to find the derivative here, but I think it might be easier just to go ahead and distribute that x to the 1/3, and I think it'll make my derivative easier. So if I do that, I'll get f of x equals, if I distribute the x to the 1/3 here, that's x to the 1/3 times x to the first. Add the exponents, I get x to the 4/3. Then distribute it here, minus 4x to the 1/3. And so now that makes my derivative pretty easy just using the power rule. That's going to be 4/3 x to the 4/3 minus 1 is 1/3. Here I move the 1/3 down and it comes and multiplies with the -4 in front. So that's -4 times 1/3, that's -4/3. X to the 1/3 minus 1 is -2/3. All right. From here, I think I'm going to need to do some more algebraic steps to simplify this derivative as much as possible to make it simpler to solve it when I set it equal to 0. So let me rewrite it. That's going to be 4 times the cube root of x over 3 minus 4 over 3 times the cube root of x squared. If I get a common denominator, I'm going to multiply this by the cube root of x squared on the bottom, and I got to do the same thing on the top. So when I do that, let's see, that's the same thing, that cube root of x squared, that's the same thing as x to the 2/3. So that when and this right here is the same thing as x to the 1/3. So when I multiply x to the 2/3 times x to the 1/3, I add their exponents and I just get x to the 3/3, right? So it's just x. So that gives me, hope you're able to follow this. I'm multiplying this with this, and that's why I was doing this up here. I'm adding the exponents, and I just get 4x over 3 cube root of x squared minus 4 over 3 cube root of x squared. They have a common denominator now. I'm able to combine them into a single fraction. That's going to give me 4x minus 4 over 3 cube root of x squared. And now I'm setting that thing equal to 0. And I think what I want to do is maybe cross multiply. So like pretend this is over 1. If I cross multiply, the 0 times that term is just 0. And the 4x minus 4 times 1 is 4x minus 4. Okay, hopefully you're able to follow that. 4x minus 4, cross multiplying with the 1 on bottom here is just 4x minus 4. 0 on top here, cross multiplying with the 3 cube root of x squared on bottom here is just 0. So now I solve this, move the 4 over, divide by the 4, 4x equals 4, divide by the 4, x equals 1. So there's one of my critical points. Critical values would be x equals 1. And my other question, let me just rewrite this again. Again, my derivative, if I write it in a simplified way, is 4x minus 4 over 3 times the cube root of x squared. The other question is this undefined anywhere? And yes, it is. It's undefined when x is 0. If I plug in 0 for x, I'm going to get a 0 on the bottom. So it's also a critical point at x equals 0. So going back to my presentation here, that's what this says. F prime has a 0 at 1 and is undefined at 0. So we will make intervals. The intervals will be negative infinity to 0. So that this 0 and this 1 split my domain up into intervals. Negative infinity to 0 is one interval. 0 to 1 is another interval. And then 1 to infinity is the final interval. And so the function is going to increase or decrease only over those intervals. Those are the only possibilities where it could change from increasing to decreasing or vice versa. So those are going to be our test intervals. We're going to test values within those intervals. So what should we test? If one of our intervals is negative infinity to 0, let's test something within that interval. A simple thing might be to plug in negative 1. Plug in negative 1 into the derivative and see if it comes out positive, negative, or 0. Plug in, and then we got to test something between 0 and 1. Well, let's try 1/2. Plug in 1/2 into the derivative. And then between 1 and infinity, let's find a number there. How about 2? Let's plug in 2 to the derivative. All right, so if we plug in negative 1, just use your calculator. Plug in negative 1 right here, and we get negative 8/3 when we do that. So that's negative. That means the function is decreasing from negative infinity to 0. Plug in 0.5 or 1/2 into the derivative. If you do that again in your calculator, you get somewhere around negative 1.06. So it's still negative. The derivative is still negative over that interval. So it's still decreasing. And then the final test point is going to be 2. If we plug in 2 to the derivative, we get something around 0.84, which is positive. So that means the function is increasing on this interval. So let's summarize that. That means that the function is decreasing from negative infinity all the way to 1. Since the derivative was negative on both of those test intervals, that means it's decreasing that entire time. It's decreasing from negative infinity to 1, and then it increases from 1 to infinity. And those are my intervals of increase and decrease. All right, let's continue that. One more note here. Note that no endpoints on that previous example, that there are no endpoints or no endpoints for a restricted domain are given. So that's what we said earlier. It didn't say like, oh, on the interval -1 to 5 or something like that. It just gave us the function, which meant we were evaluating that function over the entire domain, -infinity to infinity. Since the function changes from decreasing to increasing at x equals 1, that means if it changes from decreasing to increasing, the only time it can change from decreasing to increasing is at a local minimum, a relative minimum. That means 1, -3 is a relative minimum. We now know that. And all we had to do was algebra. We didn't have to graph it in our calculator or see a graph or anything. Furthermore, since this is the only turning point for the function, it is also an absolute minimum. So there was no other turning point. Let me see if I can sketch that for you. All right. -infinity to infinity. All right, it was decreasing over the entire time from -infinity all the way to 1, right? At 1, it changed to increasing. Now, it might have had some things like that in there. It might have been done some extra curving, but it never did turn back up until it got to here. And so that means that that thing has to be a local min. And again, since that's the only turning point, it is also an absolute minimum. All right. We will let that be the end of part 1 for this curve sketching lesson.